Co-authors on this talk, Dr. Mark Geary and several students that I've had the privilege to work with over the years. I'll pick up first where Dr. Epstein left off, then go into a few past examples of fully digital arrays, then speak to the trait spaces and architecture surrounding the processing and I/O between multiple subarrays. Quickly go over some adaptive beamforming and calibration concepts, and then finish with an example of how adaptive beamforming and calibration can in principle be traded off in terms of complexity at the system level. So as the previous speaker mentioned, the history of phased arrays has moved from single transmit, single receive type of phased arrays with lossy analog beamformers through to solid state analog beamformer front ends with multiple receivers and multiple waveform generators to give moderate beamforming performance and more graceful degradation. The future / now is a fully digital array where every single element has its own transceiver and or analog to digital converter and direct digital synthesizer or some sort of transmit firmware and hardware that's connected in some way to a digital backend, ultimately to a processor and controller. And what this promises to do is, we'll talk about that on the next slide, but the immediate challenge is how do you deal with the cost, size, weight, and power issues associated not just with having a transceiver and an analog to digital converter at every element, but all of the I/O and beamforming issues that show up in a digital backend when you have potentially thousands, tens of thousands, or even hundreds of thousands of elements. So why would you want to do this? Why would you want a digital element, digital phased array with digital at every element? The main thing is it gives you ultimate beamforming flexibility to do, at the very least, simultaneous receive beams, limited only by processing and I/O and not by the number of parallel analog beamformers. But it can also let you do simultaneous transmit beams with a suitably flexible transmit architecture. And MIMO, multiple input, multiple output, is a generalization of that. Also lets you do adaptive beamforming with dynamic degrees of freedom. You can extend that all the way to the element level. In a large array, of course, that's computationally expensive, and I/O is even more of a big challenge, as we'll see in just a few slides, with element level adaptive digital beamforming. But it at least gives you the capability of doing that with suitable advances in computational resources. It also gives you advanced calibration capabilities with the potential for ultra-low side lobes, wideband equalization, and also self-calibration for the removal of errors associated with lower cost, size, weight, and power transceiver elements. So in that sense, calibration is an enabling technology. As mentioned before, multiple input, multiple output is possible, giving new capabilities and new application areas. One of the big advantages of a fully digital array in principle, and what it promises, is very large dynamic range improvements that can be on the order of 10 log n in decibels, where n is the number of elements or transceivers. And some of those performance metrics, and I have here all the different flavors of dynamic range you might want, are limited by correlation of spurious products in the transceivers owing to compression of front ends. And there's some interesting work going on here and elsewhere to address this and get the promised large increase in dynamic range. So in other words, you might have a 55 or 60 dB dynamic range at the element level that scales with 1,000 elements up to 90 or 95 dB. So very, very briefly, just going through some history, there was work in the 80s and 90s in building offline process, just capture waveforms and store it and then process it later type of multi-element digital arrays. By the 1990s, that had moved to hundreds of narrowband channels, mostly in card and rack-based form factors. By the early 2000s, a couple different groups had started integrating digital receivers with 25 or 16 elements onto sets of panels. At about that time, ONR started working on their digital array radar in the late 2000s, associated with an Affordable Common Radar Architecture, or ACRA, that featured real-time FPGA processing. So no longer need to store the data and post-process it, but actually forming digital beams in real time with digitization at the element level. This is when I started working on my the project I had as a graduate student at Purdue, the Army DAR program, where we basically, with DigiKey level components, hand assembled a 16-element digital array with about 20 megahertz of instantaneous bandwidth that had 16 elements to it. And there's similar test beds that showed up at about the same time at X-band for sense and avoid applications on UAVs. And since then, there's quite a bit of work going on to not replicate, but to extend this concept and just generate more test beds that are similar to this. At about the same time, the Air Force was working on their transformative element level array with extremely wide bandwidths, instantaneous bandwidths of 500 megahertz plus from 2 to 18 gigahertz. Again, going back to card and rack based form factors for those types of bandwidths. Mention also a lot of digitized subarrays or arrays where there's a number of analog beamformed elements that then get digitized, like the aforementioned square kilometer array. A lot of those still feature many digital channels, leading to not gigabits or terabits, but petabits per second of data that's actually being processed. Just a few more notes. Previously, Dr. Epstein had mentioned the CFAR in Australia and the Space Fence, which is currently under development. There's also a system out of Israel that's been fully digital for about a decade now, and FlexStar is also under development. Several test beds are being developed, known test beds, one at AFRL, one at Johns Hopkins University Applied Physics Lab. Aforementioned DARPA ACT programs, I'm working with the Rockwell Collins team, and this is just a block diagram of the common module, which has 16 digital receive elements and one degree of freedom on transmit using reconfigurable silicon germanium in the front end, very low power analog to digital converters, and an ARIA-10 FPGA. We here at the University of Oklahoma are also working on a 1,000-element digital array that we're calling Horus, featuring gallium nitride front ends, CMOS transceivers that include all of the analog and digital conversion functionality, and then hooked up to, again, mid-grade commercial FPGAs. So there are several of these digital arrays currently under development. I'll go through the math quickly and leave the details for the paper, but I wanted to point out some of the most important salient features of how you might design the processing and I/O associated with these arrays. First thing to note is that if we're forming P-beams in the frequency domain, you can represent that as a linear combination of all of the element signals, these X sub m, or all of the element responses, X sub m. And you're imparting an equivalent amplitude and phase at a given frequency to each one of those elements through something that could be written as it is here as a finite impulse response digital filter. This is a generalization, and these are equivalent responses. The point here is that each of these receive channels has not only an element pattern, which in a large array can be approximated using traditional phased array means, but over a wide enough bandwidth, you get a linear receiver model that includes channel gains that are temperature and frequency dependent. And the process of calibration deals with non-idealities in this G term as well as this F term to impart an overall array response that you get as a function of frequency for a fixed angle. So the processing that needs to happen is the aggregation, for one, the summation, and also forming and actually doing the processing either in the frequency or time domain. To do that, you need to at least know something about these G terms, in other words, phase non-idealities, amplitude imbalances, and things like that. And that generalizes to the process of equalization. Simplest case being, you set this H filter term to be 1 over GM to undo whatever is the complex error associated with GM. And this can all be subsequently processed with adaptive digital beamforming to remove residual errors and steer very precise nulls in particular directions. Just a few examples of systems I've worked with in the past doing these calibration. type processes, going from what you might get with an analog array, where the best you can do is alignment at a particular scan angle, leaves you with kind of unsatisfactory side lobe levels, even if you try to taper cross-polarization issues in this case. Whereas if you know the precise amplitude and phase of embedded element patterns, you can drive the side lobes down and get very, very precise copole and cross-pole behavior. We also have a cylindrical digital array here at OU that we've been playing with very, very strange and non-ideal embedded element patterns that precludes the use of Fourier type analysis to figure out what the patterns are. But because it's a digital array, we can still drive the side lobes down quite effectively. A few notes on front-end processing, how you actually achieve these various processing components. For a direct conversion system, in other words, straight to I and Q at baseband that then gets sampled by 2 analog to digital converters, you can relate this frequency domain behavior that you're trying to drive directly to the FIR filter coefficients through a discrete Fourier transform. Whereas in an IF sampled system like we're doing for DARPA ACT, we have to deal with frequency offsets and frequency shifting and phase scaling and amplitude scaling as well. So it's not always a direct relationship there, but there is an equivalence at the end of the day. And for wide bandwidths, you might need to do true time delay beamforming, where you're imparting a frequency dependent phase shift as well. So that drives the number of taps that you might actually need here, or the complexity that you're able to get, or the resolution and frequency if you're doing a sub-banded type approach. What's more of a concern, immediate concern when talking about a large number of elements, is how do you aggregate all of this data and reduce it to a smaller number of essentially data pipes going into a final processor. As mentioned in the previous talk, hierarchical and systolic architectures are an option. Hierarchical beamforming means that you take a digital front end, which may consist of multiple elements, put that through an intermediate processor that aggregates the signals of these elements, and then it sends it down to the next stage, et cetera, et cetera. And you're limited then by the final bandwidth, beam bandwidth product you can achieve on this final link going to the final data node or processor. In a systolic array, it's a generalization, it's a special case of a hierarchical beamformer where everything is sent down a single line. And this, of course, has some latency and memory issues associated with it, but it is much fewer interconnects to get the same total processing. You can distribute this, logically distribute these summations out into further summations over the digital subarrays, each one of these distributed front ends, having their own processing associated with them, followed by subsequent processing at the distributed front end level in the intermediate processor that could be doing things like true time delay and or adaptive digital beamforming. And this is the typical construct that these digital arrays actually use.